Okay, let me introduce the support lemma here. Basically, the support lemma says that if I have a random variable x, I'm consider the alphabet of x with this script x here, and consider all the distribution of x. Let me rotate it, denote it with this script px here. For example, an element of this px will be this px here. That's basically PMF, the probability mass function of this x here. Now, if I have some functions, like let's say k function f1 up to fk, such that it map the distribution of x to a real number. For example, like this fi can be an entropy function. So it's a function applied to the distribution of x instead of applying to the x itself. Now, if I think of mu as a measure over px, it's just think of like mu is a distribution of x. And I compute the expected value of its fi given the distribution of this measure, given the distribution of x. I assume this is fixed to be this expected value FIP, so therefore this is equal to this integral FIP mu dp. Then what the lemma said is that instead of thinking of this mu here, it's sufficient for me to just find k pj, that's p1, p2 up to pk, basically like k distribution of x, and this expected FIP all can be written as converse closure of this FIPJ. Okay, it's a little bit mouthful, honestly, but let me give a proof, and then I will give an example. Hopefully it will be easy to see why it's so. So let me define fp as f1p, f2p, and f2fkp. So this is like fp is like a vector. It's a vector composed of or this like components here, and so what we have is like px is connected and compact, because think of what is x, what is px here. All the distribution of x is the PMF, and we can change this x. For example, the PMF can be I have k value, I can have like 0.1, 0.2, something like that. Let's say some values, 0.1, for example. This is all sum up to, supposingly, this is a PMF of x, and an element of this px. Supposingly, this should sum up to 1. And I can change tiny little bit of this guy here, and maybe decrease tiny little bit of this guy here, and still all this sum up to 1, and it's still an element of this px here. So apparently this will be like connected. Actually, I don't need it to be compact, but let's say it's connected. And then since it's connected, then f is continuous. Actually, I think I mentioned that this is continuous. If f is continuous, then this fpx here is also connected and compact. So let me denote this set as R. So what happened is that I only have, because it's all connected, this R is only one, has one connected pieces, and it's less than k. So what happened is that we can use the second case of the Carathéodory theorem. It's basically saying that if we have less than n connected component, disconnected component, so we only have one connected component. If I have a vector of size k here, then if I have something is like converse closure, any elements to be converse closure of this k-dimensional element here, then I only need k points in this FP, such that like any point will be a converse closure of this k point. So let me just go through this here. So I have let's say mu is a measure over px. Then I denote this expected fp. Now p is like a random variable. Will be like this: expected f1p, expected f2p, and so on, expected fkp. And then like this, basically this expected f1p and so on is just defined as this guy here. Then this k-dimensional point here is basically a converse closure of this set here, set of points at fpx here. Now then immediately by curve all the way to we can find k points in this R and alpha 1 up to alpha k, such that each of this fp will be a converse combination of these k points, and this k points is just this f1p pj. For example, the j point will be f1pj, f2pj, and so on, fkpj. And immediately we will have like expectation FIP is equal to the converse combination of FIPJ. And that's the proof basically.